Hello everyone. So this is the first video on linear algebra. We will discuss in this class what is a vector space and what are the properties of the vector spaces and what is a subspace, and we will solve some problems on the subspaces in the first two videos. So first thing is, what is a vector space? See, when coming to the context of the vector spaces, two things you must keep in mind. First thing is vectors as well as scalars. For example, I have a vector of length, let me say 3 centimeter. Can I make it 6 centimeter? You will say, sir, scale it twice, 2 times this, right? So it will be 6 centimeter. That is 3 into 2. This 2 is nothing but scalar. It doesn't have any direction. Whereas vector has direction, in which direction it is moving. That's a vector quantity. Likewise, there are vectors as well as scalars. So these two associated with some operations, they will form an algebraic structure called a vector space. Let me discuss what is a vector space first of all. So here I will consider the set of all vectors with respect to addition as well as multiplication. This addition is nothing but addition of two vectors, right? So if two vectors are there, A and B, already we know by law of parallelogram law. So this stands for the resultant vector A plus B. Sum of two vectors is given by the parallelogram law. That means you can add two vectors by parallelogram law. So addition is you have that provision to add two vectors. So that's why I included this. And what is this multiplication? That is the scaling. So two properties are there. This and scalar, right? Since once we add two vectors means it's internal, right? If you want to add any two vectors or else any two objects here, we will consider two vectors. That means they are from the same space or else same set. So this composition is called internal composition. That means adrogade irodu. Vector add ಮಾಡ್ತೀರಾ, so they are adrogade ಇರುತ್ತವೆ. That's why it's called internal composition. What is this scalar multiplication? This is called as an external composition. Why it is called external composition? ಯಾಕದನ್ನು external composition ಅಂತ ಕರೀತಾರೆ ಅಂದ್ರೆ, you will scale by some other quantity from the field. The scalar is from a field F. It may be real or complex or any field. So you can consider that fellow from any field. ಅರ್ಥ ಆಗುತ್ತಾ? Or else you can consider ZP. ಆ ಥರ ಯಾವುದಾದ್ರೂ field consider ಮಾಡ್ಬೋದು. So in that sense there are two composition. One is internal composition, other is external composition. Internal composition means vector addition, the other is scalar multiplication. Is it clear? Okay. Now, how to think about this when we say that it forms a vector space? First and foremost thing is, what is the demand on this V with respect to addition? Is it clear? V is there associated with addition as well as multiplication. That is internal composition. So what are the demands for this internal composition? First thing is, it must be an abelian group. Right? Abelian group means 5 properties must be satisfied. Closure law, associative law, and existence of identity, inverse, commutative. This property must be satisfied by this. The idea is clear. Second thing is, see, alpha is any scalar and V is any vector. Then if I scale it, it will be in V. For example, 3 centimeter is there. I scaled it by 2. So 6 centimeter, I got a vector. This was a vector. I scaled it by that. So this is V times alpha. It is again a vector. Getting my point? The resultant will be a vector. This idea is clear. You can scale them. You think about an antenna which used to be, you can flexibly move, right? If antenna is there in some golden if you just look into some old radios or else old televisions also has antennas that you can scale it, right? You can shrink it or else you can expand it. So it's an scaling quantity. It will be, again, it will look like a vector. So that visualization should be there in your mind. Then alpha into V1 plus V2, that is, you add two vectors then scale it. It is nothing but scaling and adding. That must be satisfied. Fourth thing is, add the scalar quantity and then multiply to the vector. It is nothing but scaling and adding. Idea is clear? They have that feasibility. Then alpha beta times V equals to alpha beta V, where alpha beta everything are scalar. We will just write all those things all at once. Then 1 into V must be equals to V, where 1 is an element from the field F. 1 stands for unity. If you are dealing with matrix, this will stands for 1 0 0 1. So it doesn't say only exactly equals to 1. It means an identity element. If you multiply to the vector, you will get the same vector back. And alpha beta are from the field F. V1, V2, V are the vectors. So how many properties are there? If it is an abelian group, 5 properties are there. Again, this is the sixth property, 7, 8, 9, 10. So it must satisfy these 10 properties. Then we say that if this V with respect to internal composition and external composition satisfies this property, where the scalars are taken from the field F, then we say V plus and this external composition forms a vector space over the field F. And we write V is a vector space over the field F. This idea is clear, or else V is a vector space over the field F. Or else we will write V of F. These are the notations. Okay, some author will use any of this. Now, we move on to some properties of this vector space, and we will just look into some examples. First remark is, the first property is, a field is a vector space over its subfield. That means, look to this, R is there, Q is there. So Q is a subfield of R. That means this is smaller. This set is, if you just consider the set of all rationals, the Venn diagram will look like this. So Q is contained in R. That means Q is a subfield of the field R. So R will form a vector space over its subfield. That is the remark 1 that we observed. Or else you can think about C. It will form a vector space over R. Or else you can think about C will form a vector space over Q, because Q is a subfield of C again. We will just bother about the fields. Is the idea is clear? So that must be clear to you. Then Rn is a vector space over R, or else Cn is a vector space over C, or else you can think about Cn is a vector space over R. Likewise, so Fn in general is a vector space over the field F. How does the elements of this Fn will look like? It look like n tuples, where each A is from the field F. Idea is clear? So these are the standard examples. Then again is, look to this, R is a vector space over C. Instead of considering this, I reversed it, whether this will form a field. No, it never happens. Why? Because you think about the external composition. That is the property 2 that we mentioned here. Take any element from the field F and a vector, okay, from the vector space. This is V and this is F now. We don't know, we are checking. So I took an element, some root 2 from the real and I from the complex. That is the field F. Then root 2 into I must be in R. Whether it is in R? No. Root 2I doesn't belongs to R. That means scalar multiplication is not possible. External composition does not agree. That means R is not a vector space over C. Similar to that, you can think about Q is not a vector space over C, or else Q is not a subspace over R. You take any real number and multiply to it, you won't get a rational. There are some instances where you get a real number itself. It cannot be rational. If you take any complex number, some I into rational number 3 by 4, let me say. So it will be 3 by 4 into I, which is not rational. Likewise, this and all doesn't forms the vector spaces. This idea is clear. Next example is, if S is any non-empty set, S is any non-empty set, then F be any field. S is non-empty, F is a field. Consider the set of all functions. F is a function where it's a function from S to the field F. Then V is an vector space. Vector space over the field F. You can think about anything. You consider F1 and F2 belongs to V and alpha belongs to F. You try to think about all those 10 definitions, it will work. Right? It will form a vector space. So, in particular, instead of S, if I take S equals to N and F equals to R, what will happen now? V is set of all functions from natural number to real. It's nothing but real sequences. V is nothing but real sequences. It will form a vector space over R. So V forms, and that is set of all real functions, real sequences, will form a vector space over R. Instead of R, you consider C. Fifth example. So this is nothing but complex sequences that will form in vector spaces over C. This idea is clear. So sixth example is set of all polynomials of degree less than or equals to n over a field F will form a vector space. But some author will use set of all polynomials of degree less than or equals to n. For 0 element, that is 0 polynomial, degree is not defined. We will come to that while discussing the rings and field theory. However, set of all polynomials of degree less than or equals to n over the field F, it will form a vector space. Some author will use this as specifically set of all polynomials of degree less than or equals to n, including 0 polynomial. Because once he is speaking about the degree, means for 0 polynomial degree is not defined, so he will include. But however, if we say set of all polynomials of degree less than or equals to n, it's understood that 0 polynomial is also considered, because it must form an abelian group. 0 element must be there. This idea is clear. Next thing is, if V is a set of all matrices of order n cross m, where the entries are from the field F, it will form a vector space. This idea is clear. It will form a vector space over F, or else any subfield of F. The idea must be clear. Okay. Now there are some properties on these vector spaces. We will just list those properties and we will solve some problems. Properties are this. So this is an 0 vector, you multiply a scalar, you will get 0 vector itself. 0 is the scaling quantity. If you multiply a vector by a 0, it will nullify that vector. So it will be 0. Next thing is alpha into minus v is nothing but minus alpha times v. Minus alpha is v, alpha into v is minus of alpha v. The same thing. Again, alpha times v1, v2, it is distributive. Again, alpha into v equals to 0 means either this is 0 or this is 0, or both of them may be 0. That is different. At least one of them will be 0. That's what I mentioned here. Cancellation law, this plays an important role while just looking to some examples, or else to know whether it's a vector space or not. So I stress this. Alpha and beta are scalars and v is a non-zero vector. If alpha v equals to beta v means this is non-zero vector, so that will cancel and alpha will give us beta. Here alpha is non-zero, v1, v2 are from the vector space v. Alpha v1 equals to alpha v2 implies since alpha is non-zero, that will get cancelled and v1 equals to v2. Right? This cancellation law, kindly think about this. We will solve that. While solving the problems, we will utilize these results. Then the set of all real valued continuous functions, differentiable functions or integrable functions defined on the interval closed interval 0, 1 will form a vector space over the field F. That field F is set of all real numbers. The set of all convergent sequences, if it is real, it's a vector space over the field of real numbers. If it is complex, it's a vector space over the field of both complex and real, because it will form a vector space over its subfield. So set of all convergent real sequences will form a vector space over the field of R. The set of all convergent complex sequences will form a vector space over the field of both real numbers as well as complex numbers. Idea is clear? So we will examine this problem. So first thing is whether it's a vector space or not. See, basically sometimes, to be very precise, there are two things to look into. Once we discuss this kind of problems, there are two things to keep in mind. First thing is, while solving the vector spaces, whether it forms an abelian group with respect to addition, if not the other conditions of scalar multiplication. So here, with respect to the addition, look to this. With respect to abelian group, there will be not a problem. With respect to other things, there will be problem. X comma y plus x1 comma y1 equals to what? X plus x1 comma 0. C into xy equals to cx comma 0. We will check this whether it forms a vector space or not. See, here with respect to abelian group, I am not thinking there is a problem because it satisfies all the properties, but here somewhere I am thinking there is a problem. C into xy equals to cx comma 0. So 1 into x comma y should give me x comma y. That is the property we discussed. It is 1 into v, we must get it as v only. So here vector is an ordered pair. So what we will get? Take c is equals to 1. 1 into x comma y, I will get it as 1 into x comma 0 according to this result. But it is not equals to x comma y. So this is not a vector space. Here look into this. This I am not going to this. I am just considering this. Of course, there are some problems where there is a problem with this also. We will encounter that also. But for this second one, c into x comma y equals to mod cx mod cy. Take c is equals to 1. 1 into x comma y will give me x comma y. But minus 1 into x comma y will give me x comma y. By cancellation law, I will get, if x and y are non-zero, then I will get 1 equals to minus 1. Howda? If I just cancel them, I will get 1 equals to minus 1 because x comma y, 1 into x comma y equals to x comma y, that is equals to minus 1 into x comma y. So you just neglect this. Then since x and y are non-zero, it will get cancelled. So 1 equals to minus 1, a contradiction. That means this is not a vector space. Again, think about this same thing. 1 into x comma y, I must get as x comma y, but here 1 into x comma y, put c is equals to 1. I will get 0 comma y, which is not equals to x comma y. So this is not possible. How about this c square y? Same thing. Put c is equals to 1 and c is equals to minus 1. You will get 1 into x comma y equals to x comma y. Minus 1 into x comma y equals to x comma y. So since both are equal, assume x and y are non-zeros, non-zero vectors. So 1 equals to minus 1, a contradiction. Getting my point? So this is not a vector space. How about this x comma y, x1, y1 equals to x comma. See, here there is no problem with this, but problem is here. I've just find x comma y plus x1 comma y1 equals to what? The first coordinate. Then x comma y plus x2 comma y2 will give me x comma y. Let us assume x1 comma y1 is different from x2 comma y2. But adding x comma y to x1 y1, I am getting this. Adding this to this, I am getting the same. That means this must be equal. But according to our assumption, that is not equal. x1 y1 not equals to x2 comma y2. Simple as a plus b will give me a. So a plus c will also give me a. That should imply me b equals to c. Getting my point? Or else b and c are equals to 0. But here you add anything to it, the operation is defined, you will get this. That means this may be unequal also. So it's not additively closed. This idea is clear. So this won't form a vector space. So we will think about the subspaces and we will solve some problems on the subspaces in the next class. Thank you.